Okay, our last topic in this chapter is common units. So on the screen you do see the common units and what the metric system uses for each one of these. So for mass, metrics uses the kilogram or kg, which is a little bit larger than what we use in lab. Our lab is usually grams. Length is usually the meter, m, like the meter sticks. Time is s or second. Temperature is going to look new for you. You might be used to Celsius, but I will show you how to convert to Kelvin, which is the metric standard for temperature. So I'll explain more about that in a little bit. And volume would be L or liter. Okay, now just some descriptions of each of these. Mass means the quantity of matter in an object. For example, gram, kilogram, milligram. And I just gave you some examples. A 120-pound person would be approximately 55 kilograms, and a nickel on the smaller scale would be about 5 grams. So just to give you some comparisons. For length, we're talking about distance. So you might be familiar with kilometer, that's a large distance, meter, like the meter sticks, and then we have centimeter and millimeter like on our rulers. So an average male height is 1.8 meters, so almost 2 meter sticks, it's almost 6 feet. And then on the smaller scale, you have the diameter of a quarter, which is the distance across, 2.5 centimeters. And the thickness of a dime is about 1 millimeter. Volume. Volume is the amount of 3D space occupied by a substance. And this is based off a cube, because a cube has 3 sides, length, width, and height. And you usually multiply those to get your volume. But for a liquid, though, volume is measured in milliliters. So like 2 liters of milk, usually in the stores you buy them in gallons, so that's a half gallon. And actually your cans of soda do say 12 ounces, but if you look on there, the milliliter is present, and it's approximately 360 milliliters. So it's centimeters cubed for a solid, and liter or milliliter for a liquid. Alright, now here's temperature. Okay, if you watch the weather, you will hear temperature given in Fahrenheit. In other countries and in our science lab, your thermometers measure Celsius. And then we have what's called Kelvin, which is what the metric system uses. You will use Kelvin later in our gas law chapter, but right now we would just like you to understand what this means and why it's important. So if you look on the screen, this is not in your notes, just in my slide here, you see Kelvin versus Celsius versus Fahrenheit. And just check out the boiling point at the top. You see 212 for Fahrenheit, 100 for Celsius, and 373 for Kelvin. So why is it so much higher? Well, the best place to see this is actually on the opposite scale. Look at the freezing point. 32 Fahrenheit, 0 degrees, you're used to that in lab, so that's like where ice freezes. And then check it out in Kelvin, that is 273. Because according to Kelvin, at 0 degrees Celsius, or 273 K, particles are still moving. So he determined a spot or a temperature where there's absolutely no motion. And on the scale that you're used to, this would be all the way down to minus 273 Celsius, which is 0 degrees Kelvin. So that is what the Kelvin scale is about. It accounts for absolute zero. All motion stops. Okay. Now, the conversion for this, this is a very important conversion. It's a very simple one, but you will use it a lot in the gas law chapter. It's knowing how to convert between Celsius and Kelvin. So if you have a Celsius temperature, like down here, minus 18 degrees, how do you get that to Kelvin? You add 273. If you're in Kelvin and you want Celsius, you're going to subtract. So try these for yourself, and you'll see that they work. Alright, now with units, you can put prefixes in front of them. And this first set of prefixes, you'll notice that all the letters are capital. These are larger than the common unit. So mega is 1,000,000, capital M. Kilo is 1,000, capital K. Hecta is 100, capital H. And deca is 10, or a capital D. So what I need you to understand is not necessarily these numbers, because you'll have them on the pink sheet that I provided, but what that letter actually means. So if you look at 1 kilogram, that capital K before gram means you have 1,000 times more of something than the gram itself. So these are larger units. And then you have the opposite, which are the prefixes. Which are the lowercase prefixes. So deci is the lowercase d, means 1/10, which is why you see a decimal. Centi is 100th, or 100 times smaller. Milli, 1,000 times smaller. And then micro, like the microscope, is 1,000,000 times smaller. And then nano, like nanotechnology, is 1,000,000,000 times smaller. So check this out, 1 decigram, lowercase dg, that lowercase d means that it is 10 times smaller than the gram. So capital versus lowercase, larger versus smaller units. Okay, and the last thing you need to be aware of is what is called, your textbook calls it dimensional analysis or factor labeling. I just prefer to call it converting because it's knowing how to use a conversion factor to go between different units. So just a common factor here is a dozen. When you hear the word dozen, you automatically think donuts, right? And it's usually 12. So dozen and 12 are equal to each other. And the same thing can happen in science. 1 inch is equal to 2.54 centimeters. This is a known factor. It's a known equation. So your job in this chapter is to know how to convert between these units. So let's try one. From centimeters to inches. The first thing I'd like you to do is write down the number that was given. So that's the 2.85 centimeters. Next, draw your scheme, a straight line and a vertical line. Okay, your job is to tell me how many inches are in this many centimeters. Now, centimeters is on the top, right here. You need to put centimeters on the bottom. So use this conversion factor, okay, 2.54 centimeters is placed on the bottom so that it cancels. And 1 inch goes on the top. Okay, next you need to solve, okay? And to solve this, you multiply across. So anything times 1 is just itself. And then you divide it by the bottom, 2.54. And get your answer. And make sure you round this to correct significant figures. It'd be 1.12 inches. Okay? All right, let's try one more. What if we go in the opposite direction? You have 7 inches, so write that first. Draw your scheme, and using the same conversion factor, you have inches on top, so 1 inch should go on the bottom. Y, so that it cancels, and 2.54 centimeters goes on top. Where am I getting this 2.54 from? It's up here. And now here, you multiply the top and get your answer. And in this case, you don't have to divide by the bottom because it is just 1, so you can eliminate that step. My calculator is reading 17.78, but you need to round that to correct significant figures. 17.8 centimeters. So this is called converting.